The next group of reactions we're going to be studying is oxidation-reduction reactions, also known as redox for abbreviation, and they're very, very important in biology, okay? And they're important in chemistry too. But lots of biological reactions are redox reactions, okay? Getting energy out of food is a redox reaction, okay? Cellular respiration, photosynthesis. So if you're planning on taking biology, this will help you also with that. A redox reaction involves the transfer of electrons between two different molecules. Okay, sometimes it's very obvious. Okay, you have sodium reacting with chlorine. You can separate as two individual equations. We call them half reactions, and you say, I know sodium has one valence electron that's going to lose it, so two sodium will lose two valence electrons. I know chlorine, the atom has 7 valence electrons, so it's going to gain an electron. So you can see very easy how the electrons were transferred from the sodium to the chlorine. So that's a redox reaction, and it's very, very easy to tell. The problem sometimes is not quite as easy. And let me give you an example. Let's see if I can do it without my tablet jumping up. But for instance, if you have glucose, 6,6H12O6, in the cells it reacts with oxygen, and it forms carbon dioxide and water. And I tell you, that's a redox reaction too. And you say, well, where do the electrons come from? Where do they go? Who gets the electrons? You can't tell. Okay? So this is what we're going to be doing in this chapter, studying these not so obvious reactions and seeing how the electrons are transferred, and most importantly, balancing the reactions, because it's not going to be very easy. So in the example that we was looking, we say sodium loses electrons. We call that oxidation, the loss of electrons. Okay? And that means the sodium is oxidized. This is something you just need to memorize. There's no, I don't know of any gimmick to remember. Chlorine, we say that gains electrons. We call that reduction, getting electrons. So chlorine is reduced. Like I said, this is a very easy example, but also keep in mind, when sodium loses electrons, it causes chlorine to be reduced. The reason chlorine gains electrons is because sodium was oxidized. So you could say that chlorine causes sodium to be oxidized. So there's one more term in there. Sodium is a reducing agent because it provides electrons to reduce chlorine. Chlorine is an oxidizing agent because it oxidizes sodium. If you get confused, remember that the agent that is oxidized is known as the reducing agent, always the opposite, okay? If you lose electrons, you cause somebody else to gain. If you gain electrons, you cause somebody else to give them. The agent that is reduced is called the oxidizing agent. And this is where you want to be careful in an exam. Read the questions, because they may ask you who gets oxidized, who gets reduced, or they may ask you who's the reducing agent, who's the oxidizing agent, or they may ask you both. You need to know what is being asked so you can answer correctly, right? In this particular case, you say, well, it's not so obvious because this is a covalent compound, so they're sharing electrons, right? So nobody's giving electrons, nobody's getting electrons. How do we define oxidation reduction? Well, remember we've done that before. We come up with some hypothetical number. In this case, we're going to call it oxidation number. Remember I said before, these hypothetical numbers, they have a set of rules to determine them, but once you give them, they're very useful. Remember we used them before trying to remember with formal charges, for instance. Formal charges were not real charges, but it allows us to choose which one is the most stable among several resonance forms. This is the same thing. We are going to determine oxidation numbers for every atom in every compound, and that's going to allow us to determine who gets oxidized, who gets reduced. The definition really is an oxymoron, in my opinion, because it says is the charge of the atoms would possess if the compound was ionic. Okay, but it's not. It's not ionic, so like I said, the definition is stupid. Just take my word. It's a hypothetical number that you can determine following some rules, and if you do that, then you can determine who's oxidized, who's reduced. Just as hypothetical, just as real, whatever you want to call it, as formal charges. And we're going to see things like that in chemistry every so often. It works, so we use it. That's the only explanation, really. So there's actually 4 rules. I didn't mention that, or 4 steps, but I mentioned that in there because it takes 3 slides. Okay, rule number 3 is very long, so I'm just giving you head start. This is not it. Okay, so you begin. The oxidation number of an atom in an elemental substance is 0. That means when you have an element, the oxidation number is 0. It doesn't matter as a molecule, oxygen, or maybe it's just an atom, carbon. It doesn't matter. If it's an element, the oxidation number is 0. For many monatomic ions, and many doesn't mean all, there's going to be exceptions, the oxidation number equals the ion charge. So you have sodium plus 1, the oxidation number is plus 1. You have chlorine minus 1, the oxidation number is minus 1. But there are exceptions, and that's what rule number 3 is all about. But those exceptions. Okay? These are exceptions. Hydrogen. Usually hydrogen is plus 1. This is going to be the most common. Okay? When you're combining with non-metals. But sometimes you could have like sodium hydride. Sodium is plus 1. In this case, hydrogen is minus 1. Okay? Very rare, you're not likely to run into these ones, but just keep them in the back of your mind. Oxygen, most of the time, is minus 2, because that's the ionitude form. But again, this is the most common, not the only one. In peroxides, remember we talked about hydrogen peroxide? Oxygen is only minus 1. I don't think you're going to run to superoxides. That would be minus 1/2, very unlikely, okay? But you might run into a peroxide in there. And when you combine oxygen with fluorine, you're going to get positive numbers. But we're going to see how you determine, in this case, what is the actual oxidation number of oxygen. But remember, most of the time, it's going to be minus 2. Halogens, well, fluorine is nice, minus 1. But when you get to the others, when they combine with oxygen, we just say, hey, something wrong happens when a halogen combines with oxygen, because oxygen becomes positive. And with halogens, they're going to have variable numbers, and you're going to have to determine, okay? When they're combined with oxygen, and we're going to see how you determine, okay? Don't worry about it. And finally, the last rule that's going to allow us to make those determinations, the sum of the oxidation numbers of all atoms in a molecule or in a polyatomic ion equals the charge of the molecule, which is 0, or the charge of the ion, depending on the ion. So let me give you an example. For instance, nitric acid. Okay. We know oxygen most likely is going to be minus 2, and you have 3, so you have minus 6. Hydrogen most likely is going to be 1. Nitrogen, we don't know. So we're saying that plus 1 plus x minus 6 equals the charge of the molecule is 0. So how much is X? Plus 5. Because then it will be plus 6 minus 6 equals 0. So you see, nitrogen could have more than one oxidation number, but you determine it because you know the oxidation numbers of all of the other atoms, and you know the molecule, so adding them up equals 0. Let's say you have an ion, sulfate, minus 2. And you say, well, I know oxygen is minus 2, and I have 4. I don't know this one. So I say X minus 8 equals not 0. It equals the charge of the ion, equals minus 2. So X has to be what? Plus 6. By the way, do take the time to put plus 5, plus 6, because it's important, okay? We're going to be seeing later on two oxidation numbers go up, go down. Just not assume that you don't have a sign and you're going to assume it's positive. Take the time to write positive and negative because it will be important later, okay? It doesn't take that long. So here you have some examples. Sodium sulfate is pretty much what I did before. You know, well, one of the things that you can do is to separate. If you want, when you have an ionic compound, you can do that, or no, your choice. But you can say sodium is plus 1. The sulfate ion, we just did it right now, and we came up with this the example is this. But you could also say, well, I don't want to break it into ions. And you say sodium is plus 1, so I have plus 1 times 2, plus X, that I don't know how much it is, plus minus 2 times 4, because there's 4 oxygens, equals 0, because it's the molecule. Either way, you come up with the oxidation number of sulfur is plus 6. Whichever makes more sense to you, either one will work, okay? Another example, you know hydrogen is plus 1. So plus 1 times 2 plus X. This is a molecule, so equals 0. So X has to be minus 2. You see, that sulfur is the same atom. Here it was plus 6. Here is minus 2. The oxidation numbers can vary a lot, okay? You could also say that, well, the ion is protons and sulfide, that's an ion with a minus 2 charge. So either way you want to do it. I still like better adding more up together, okay? There's less chances of making a mistake. Have another ion here, sulfide. Once again, sulfur, we don't know how much that is. Plus 3 times minus 2 from the oxygen equals the charge, that's minus 2. So this time sulfur is plus 4. It's not difficult at all to determine the oxidation numbers, okay? And seriously, adding up all of the oxidation numbers and equaling the charge of the ion or the molecule is the safest way to do it. So that allows us now to redefine oxidation reduction and redox reactions. A redox reaction is going to be one in which one or more elements undergo a change in the oxidation number. Since we can determine the oxidation number for every atom in every molecule, that becomes very easy. Oxidation means an increase in the oxidation number. So remember, we was looking at sulfur goes from minus 2 in here to plus 4. If that was a reaction, sulfur has been oxidized because it went from minus 2 to plus 4. It increased. Reduction means a decrease in oxidation number. And that's easy to remember because in English, this is not chemistry, but in English, to reduce and to decrease mean the same thing. Okay? So that's very easy to remember. Now, there are several types of redox reactions. Basically, we have combustion reactions, single displacement. A combustion reaction means burning something. So many times you're talking about oxygen, but not always, okay? The characteristic of a combustion reaction is that it's a very vigorous reaction that produces a lot of heat and oftentimes light, sometimes as a flame. And look at an example. This is solid rocket fuel. It reacts with aluminum. We're not going to study the reaction. Just take my word, it's a redox reaction. But you know it's a redox reaction because it's very vigorous. Have you seen the space shuttle take off? It produces a lot of heat, produces flames, has all of the characteristics of a combustion reaction. But there's no oxygen anywhere in there, okay? We're also going to look at single displacement reactions, a redox reaction in which a metal replaces the cation of another molecule, so now this cation becomes the pure metal. Okay? And that brings me to one of the examples I like to do demonstration in the lab of a redox reaction. You get a tube, what do you say, was silver nitrate? Yeah. So you have silver nitrate in here, that's clear, it's a solution, and copper, that's colored copper. You put in a test tube and you wait, and you really can't see much the solution. It's supposed to be getting a little bit darker, but whoever took this picture put a dark background, and I ran it through a couple of programs, and every time I delete the background, it deletes the background inside the test tube. So I just had to leave it. But you can see the copper is not so shiny. If you wait long enough, and it usually takes 2 or 3 hours, that's why we do it. We begin at the beginning of the lab and we look at it at the end of the lab. The solution is copper nitrate. And copper nitrate is blue. The solution went from clear to blue. What happened to the copper? Well, you have silver being deposited on top of it, and that's why it looks dark. So that's a redox reaction that you can visibly see the reaction taking place. Okay? Now, redox reactions usually take place in aqueous media, and that complicates things because you're going to have water not only as a solvent, it can be a reactant. There's going to be hydronium ions. Remember, hydronium ions are protons that react with water. Okay? Or maybe you have just protons, but you have hydroxide ions. They may not get oxidized or reduced, but they are part of the reaction. Okay? So you're going to have to balance them in there. They're saying it's difficult to balance by inspection is the understatement of the century. They're nearly impossible. Okay? Years ago, I made a mistake in an exam. Okay? To my defense, I was pulling the questions from the question bank from the publisher. I should have double checked because everybody makes mistakes, including textbook publishers, but I didn't. And at the time we was not doing redox reaction, I just gave the students five equations to balance. And when I got the exams back, there was one equation that everybody in the class got wrong. Well, when everybody misses a question, I go back to see, is something wrong with the question? And this time it's like, oh my goodness, it's a redox reaction. So I have to explain to the class. First, I'm apologizing because the mistake is the publisher's, but I did not check it. Second, this is not going to count. So instead of 25 questions in this exam, I'm going to get it out of 24. This is not going to count at all. Third, don't panic because eventually we're going to get to redox equations and you will learn to balance these equations. There was one student who saw me his scratch paper and he said, you told us that when we were balancing equations many times it's normal. Some atom was balanced to get unbalanced and just try and 2 or 3 steps and you get everything balanced. I said, yeah. I said, well, I tried that particular equation and I balanced something 27 times, but it kept unbalancing something else. And he gave up. That's what I mean by it's virtually impossible, okay? So the way we're going to do it is called the half reaction method. Now, I'm going to show you how to do it, but I do have a handout where it lists step by step. First you do this, then you do that. So if you sign up for Wysand, I will give you a copy of that handout. I'm going to explain to you, and you can take notes, okay? But if you want it printed out, that's very useful because you can have the directions, and when you're bunching an equation, doing homework or studying, you just follow the directions. And I've told you before, I think that's the way to learn, because eventually you stop looking, you know how it begins, you start looking less and less and less at your direction sheet, and you start doing more and more on your own. By the time you get to the end of the worksheet, you don't need to look at it. You learn it without memorizing. But again, if you want my handout, you have to sign up for Wysand. Okay? So we are going to balance this equation, dichromate ion and iron, to form chromium ion and iron. And this takes place in acidic solution. Okay? We are going to see in getting a basic solution, then there is one more factor you have to add in there. So first, you split them into half reactions. We have to the chromium. The chromate ion becomes chromium ion. We have to the iron plus 2 becomes iron plus 3. Now we're going to balance all of the elements except for the oxygen and hydrogen. Okay? So you go to iron and say, I have one iron, fine. I have two chromiums, so I have to put the 2 here in front. That's what I'm balancing now. Okay? I balance the iron and the chromium. Then I balance oxygen atoms. But you cannot add oxygen out of the blue because where does it come from? Now, the solution takes place in water, so I can add water molecules. Some of the water molecules from the solvent are going to participate in the reaction. So, since I have 7 oxygens, I need to put 7 water molecules to balance the oxygens. One thing I tell the students is when you're doing this, you need to figure what you're adding. In this case, we're adding water. Which side do you add it? Well, if you have oxygen on the left, you have to add the water on the right, okay? Because, once again, students get overwhelmed with these kind of reactions until they practice and they will put the water on the other side. No, because then you have 14 oxygens and none on the other side. Go slowly, take your time. It will get better with practice, I promise. So we balance the other atoms, we balance the oxygen, now we balance the hydrogen. Once again, the only thing you're going to find in solution is protons. Okay? There's always protons because water dissociates itself. So, since we had 7 times 2, 14 hydrogens, I have to put 14 protons in there. At this point, the iron is balanced, the chromium is balanced, the oxygen is balanced, the hydrogen is balanced. So, we are doing good. The next problem is going to be balancing the charges. You're going to add electrons. You cannot add positive charges because positive charges are protons, so you'll be adding hydrogen. The only thing that will not affect the atoms is going to be electrons. Now, when you add electrons, this is where you have to be very, very conscious. Where do I add electrons? Add them wherever you need negative charges. If one side is more positive or less negative, that's the side where you want to add electrons. How many? Until the charges equalize. Okay? So, for instance, in the iron, you have iron plus 2 on one side plus 3. You're going to add the electron to the plus 3 side because it's more positive. And now you bring the plus 1 to plus 2 and the charges are balanced. When you have a big molecule, you have to look at the overall charge of the molecule. Okay? So, the total charge, this one is going to be, I need to show you the whole equation. You look at the whole reaction. So you have 2 negatives, 14 positives. So that means I have 12 positive charges, right? On the other side, I have 2 times 3, 6 positive charges. So how do I go from 12 positive to 6 positive? I add 6 electrons. But you need to look at the charges not of the molecule, but the charges of the whole left side and the charges of the whole right side. Okay? That's very, very important, because if you look at only one, the charges will not be balanced. Once again, this is more positive, so we put the electrons on this side, and we put enough electrons, so 12 minus 6 equals 6. So we balance all the atoms, we balance all the charges. Now the problem, each of the reactions has a different number of electrons. We're having a transfer of electrons. Every electron has to come from somewhere. We need 6 electrons, but this reaction only gives us 1. So what do? We multiply this whole reaction times 6, so it produces 6 electrons. So when I multiply times 6, I have 6 iron plus 2, 6 irons plus 3, 6 electrons. Now you have the same number of electrons that are lost and are taken. So we have balanced what I call the other atoms, we have balanced the oxygens, we have balanced the hydrogens, we have balanced the charges, we have balanced the electrons. We are ready. Now we can adapt these two. Just like we took the original equation and split it to half reactions, now we can recombine them to come up with one overall equation. And when you add them, everything that was on the left side, arrow, everything that was on the right side, now you can say, well, some things can be cancelled out, like 6 electrons. Sometimes you can have something, you may end up with one molecule something. So simplify the equation as much as you can. Okay? In this particular case, you're done. Do you have an example of? Yeah, you can just look through the atoms and make sure they're balanced. No. Let me make a comment, because it is in the handout, but I didn't put it in here. What if you are in basic solution? In basic solution, you do 1 through 7. But you notice that there's always protons. So you neutralize the protons with hydroxides. How many? Depends how many protons. In this case, if this was in basic solution, since there's 14 protons, it would take 14 hydroxides. That means when you have a proton reacting with a hydroxide, you form a warm molecule. So you're going to end up with warm molecules probably in the opposite side of the reaction from the ones that you already had in there, and you have to simplify the warm molecules. Okay? This is what you do. You balance it as if it was an acidic reaction, but it's not acidic, it's basic. So you cannot have protons in a basic reaction, neutralize them with hydroxides, and simplify the equation again. Okay? Like I said, if you get my handout, it will tell you, and the acidic reactions, you stop here. Basic reactions, you continue. So everything is in one page where you can have the directions. So if you like to work one-on-one, if you want to get the handout I've been telling you, if you want to get any of the sample, I'm not quite sure, maybe like 8 redox reactions, 4 in acidic conditions, 4 in basic conditions for you to practice. Remember, the advantage of practicing with me is that I will point out any mistakes, but I don't give you a grade. So you figure out where you made a mistake, and then when you're doing it at school, you don't make that mistake because you already learned it. Okay? So if you want that, go to the video description and make an appointment with me on Wisant, and I'll be glad to share that handout and the worksheet and help you in any way I can.